In this video, we'll talk about minimal spanning trees. So, a spanning tree is a subgraph of a graph that includes all the vertices and is a tree. For example, here's your graph. Here's a couple different spanning trees. You could take this top vertex and connect it to each of the other vertices. That would be a spanning tree. We've included all the vertices, and this is a tree, meaning there's no circuits, remember? And then here's another one. It can look very different. We can maybe just go around like this. We've now included all the vertices, and this is a tree. A chain is certainly a tree. Okay, that's a spanning tree. If you have a network, meaning the edges are weighted, so we can put numbers, then we can talk about a minimal spanning tree, meaning the sum of the edges of the spanning tree is as small as possible. Why would we want to do that? Minimal spanning tree uses for constructing power lines. We might have a certain cost of connecting two houses, so we want to connect that as cheaply as possible. Constructing roads, bridges, basically anytime things need to be connected, ferry routes, and there's different costs associated with connecting them. Okay, so minimal spanning trees are not a particularly difficult problem. There's two easily described algorithms that work. The first is Kruskal's algorithm, and we're going to look at this network as an example. The costs are labeled there. Kruskal's algorithm, we just start small, and we add the edge if it doesn't form a circuit with something that's already there. So what does that mean? The smallest edge is 8. We don't have anything yet, so that certainly can't form a circuit. The next biggest edge is 10. That doesn't form a circuit with what we already have, so we'll add that. Next biggest edge is 12. Also doesn't form a circuit, so we'll add that. Next biggest edge is 22. If we added that, that would be a circuit. That would be a triangle, closed loop. So we're not going to add 22. Next is 53. That doesn't form a circuit, so we'll add that. And then we stop as soon as we've hit all the vertices, which is here. And actually, we don't even need to check that we hit all the vertices. A spanning tree, if there's n vertices, there's always n minus 1 edges. 5 vertices, 4 edges. Because we need to connect every edge, not including the first one. So there has to be n minus 1 edges. So we can just stop Kruskal's algorithm once we reach n minus 1 edges. Here n is 5. Here we've added 4 edges, so we're done. There's that spanning tree. Prim's algorithm works differently, is going to give us the same result. Prim's algorithm, we start with any vertex. Let's say we start with vertex D. And then we're just going to join with lowest possible cost a new vertex. So we could do 63, 22, or 10. So we're going to pick 10. That's lowest possible cost. Okay, lowest possible cost to now join a new vertex here of all these choices is 12. Okay, 22 doesn't join a new vertex, so we've got 63, 70, 53, 54, and 53 are the choices. So we'll do 53. And then 63, 70, or 8, we're going to do 8. Okay, so a couple things to note. They're maybe not obvious, but you can figure these out if you think about them. In Prim's algorithm, it doesn't matter where you start. Think about that. See if you can figure out why that's true. And then the other funny thing is these two algorithms give the same result. differently described algorithms, but we get the same result. These algorithms are pretty good. They run in n squared log n time, where n is the number of vertices. So that's considered polynomial time. This isn't a polynomial, but log n is smaller than n, so this is smaller than n cubed, considered polynomial time. So these are pretty good. One cool thing minimal spanning trees are good for is it can help us with the traveling salesman problem. Traveling salesman problem in general is pretty hard. It can help us with a specific type, and that's the Euclidean traveling salesman problem. What does Euclidean mean? Euclidean means the weights of the network represent actual physical distances on the ground. What is good about that is that we get the triangle inequality. This may not be true of a graph in general, but if the graph is Euclidean, then the distance from A to B plus the distance from B to C is going to be at least as big as the distance from A to C. Okay. This helps us give not a solution, but a pseudo-solution. What is the pseudo-solution? Well, first you make a minimal spanning tree. So this is different costs than the example we've been using, but same look of the graph, just different edge weights. Let's just verify with Kruskal's algorithm that this is a minimal spanning tree. We start with the cheapest edge, which is 5. Actually, there's 2 5s. We can add both of them because they don't form a circuit. Next cheapest edge is 7. If I try to add this 7, it's going to form a circuit, so I'm not going to add it. I will add this 7. Next cheapest edge is 8. I will add that. And now I'm at n minus 1 edges because n is 5. I'm at 4 edges, so I'm done. So there's the minimal spanning tree. Okay. Then we're going to start at the starting vertex O, and we're going to go as far out as we can and come back. So we'll go, let's say, to D, and then come back to O, and then we'll go as far out as we can. So A, B, C, and then come back. So B, A, and then back to O. Okay, that's a pretty long path. We can shorten it. In fact, we have to shorten it because we can't visit cities twice. Okay, so how do we shorten it? We go O, D. We're not going to go back to O yet. If we went straight to A, though, because of this triangle inequality, D to A is going to be shorter or equal to D to O and then to A. So we haven't increased the length of this. Okay, so we'll go O to D to A, and then B and C we haven't seen yet, so we're good up to here. But then we've already seen B, we've already seen A, so we'll just go straight back to O. And same thing, triangle inequality, and this works with more terms too. If you go C to B to A to O, that's going to be longer or equal to C to O. So I can do this, and I have not increased, I may have decreased the cost of my path. What is good about this? Well, this one's probably better than this one, but at least the same. And then this one is at most double the cost of the minimal spanning tree. What's good about that? Well, the solution to the traveling salesman problem has to be at most the cost of the minimal spanning tree. In fact, it's going to be more. So this path is at most double the cost of the minimal spanning tree. This one's equal to or shorter than it, so it's at most double the cost of the minimal spanning tree. So we have found a solution to the traveling salesman problem that is at worst twice the minimal cost. Not great, but it's something for a solution, for a difficult problem that doesn't have an existing solution.